Okay, example 4 in our optimization chapter. A rectangular storage container with an open top is to have a volume of 20 cubic meters. So this starts off just like the last problem. Like example 3, we have an open container that we're trying to build, right? The length of its base is 4 times its width, so they did that kind of thing too. It said 3 times its width in the last problem. Now, this is where it changes. The base materials cost $9 per square meter. The sides cost $4 per square meter. Okay, so we have 5 sides to this box. We have a bottom, we have 4 walls, right? And the bottom material is more expensive than the wall material. Maybe we're shipping something very heavy, and the bottom material has to be stronger, so it's going to cost more. The side material doesn't have to be quite as strong, so it doesn't cost as much. And our job is to find the cost of materials for the cheapest such containers. So what we want to do is create a cost function for this thing. And what we have to do is understand how the cost is created in this problem in order to do this. For me personally, I would probably create some sort of a graphic organizer for this. I've got 5 sides I've got to deal with, right? So let's deal with those 5 sides. We have the bottom, so we'll call the base. And we have the front, back, left, and right. So that's how I'm going to describe the 5 sides of this box. I'm also going to draw a picture of the box. I'll do that over here. Your basic rectangular box. There's my rectangular box. We'll have to major in 3D perspective drawing in order to do this. But you just draw a square or rectangle here, just angle off 3 sides the same, and then do that. If you really want to get creative, you can do a dotted line going this way, and a dotted line coming down, and a dotted line coming across like so. Kind of see the back and everything. So there's our box. And looking at that box, I've got the bottom is down here, and the length of the box, that would be this side here, is 4 times the width. So if I call this the width, this is the length, and then we have the height. So if we can kind of draw a picture of the box, and that establishes what each of the sides looks like, right? And looking at this, we have, I'm going to make some columns here. I'm going to make one column that says area. I want area because $9 per square meter, $4 per square meter. They're giving us cost per area, right? Square meters is area. So knowing what the area of each of these sides is going to be helpful. Cost per square meter, and then total cost. Okay, so if something costs $9 per square meter and I have 10 square meters, that's 10 times 90 is $90, right? Or 10 times 9 is $90, right? That's what's happening here. I'm going to get an area expression. It's going to use the letters, though, to find the area of each of these pieces, right? I know how much it costs per area. Multiply the area times the cost per square meter to get the total cost. How much each of these sides is going to cost me. All right, and the front, back, left, and right all have the same cost per square meter. This is $9 per square meter. But I do have to find 4 areas here and get 4 costs here. Okay. I didn't use any kind of scientific method or anything to come up with this graphic organizer. I understood how the cost is being established, and I'm making up a little organized way of figuring out the cost of each piece. If I add up the total cost of each side, whatever I get down here is the total cost of everything, right? So let's make this happen. The base is, what are the dimensions of the base? The bottom. The length and width of the base. According to my picture right here. W and 4W. So if I multiply those together, 4W squared is the area of the base, right? If I multiply 4W squared times $9 per square meter, I'm going to get 36W squared is exactly how much the base of this thing is going to cost me. And as of right now, I haven't figured out what W is, so I don't know what that is, but I got a variable expression representing how much the base of this thing is going to cost. The front dimensions are what? H and
W.
W, right? Each one of these up and downs is an H, right? So W, H, so W times H is the area of the front. WH times 4 is 4. WH is how much the front's going to cost me. The back is the same, right? So WH, 4WH. The left-hand side, over here, this is 4W, this is H, right? So the left-hand side is 4W times H, which is 4WH. Multiply that times 4, we get 16WH is the cost of the left-hand side. Right-hand side is the same, right? 4W and H are the dimensions, so 4WH is the area, times $4 per square meter gets me 16WH. So the total cost of this box is going to be 36W squared plus 40WH. 4 plus 4 plus 16 plus 16 is 40, right? They're all WH's. So there's my cost function. C equals 36W squared plus 40WH. That is an accurate cost function. Is it the cost function we want to use? What's wrong with it? Too many variables. And I've got W squared, W, and H. So now I'm going to take a look, and it says it has a volume of 20 cubic meters. I'm going to use that to my advantage to get one variable in terms of the other. So if I take a look, the volume of this box is the length times the width times the height, right? So just rectangular box, length times width times height. So W times 4W times H makes 4W squared. H is the volume of this box in terms of W and H. And we're told the volume of the box is supposed to be 20 cubic meters. And again, I get, just like yesterday, I get that to say W equals or H equals. H equals is much simpler. No square root necessary. So divide both sides by 4W squared. And just like that, I get H is equal to 5W to the negative second power. And just like yesterday, negative powers are probably more useful to me in this case than 5 over W squared. Okay, they're both correct, but as far as differentiation is concerned, negative powers are easier to differentiate than fractions. So H, which is right here, can be replaced with 5W to the negative second. So my cost function can be transformed into C equals 36W squared plus. Now if I do 40W times 5W to the negative second, the 40 and the 5 make 200. And the W times the W to the negative second makes W to the negative first. So just like that, I've transformed my cost function into a 3-variable equation, cost, width, and height, into a 2-variable, cost and width. All right? I'm trying to optimize cost. I'm in a business. I want cost to be the lowest it can possibly be, right? There's millions of boxes I can make that have this dimension type, that have this volume, but there's only one that costs the least amount of money. That's what I want to make. So, once I got my function that I'm trying to optimize down to one variable, now it's time to differentiate to find critical numbers. So 72W minus 200W to the negative second power. Okay. Again, looking at these problems in the context of the problem that we're looking at possibilities of intervals, I know W cannot equal 0. For that matter, W has to be bigger than 0. So I'm going to say that W has to be between 0 and infinity. It's probably not going to be infinity. But again, there's nothing stopping a top number. I can make W 500, 4W could be 2,000, and H could be like half a centimeter. Okay, and then maybe it has a volume of 20 cubic meters. Okay, the bigger the width and the height, or the width and the length are, the shorter the height is to keep that volume the same. All right, but anyway. There's no top end stopping me, so I'm just going to go to infinity. But again, we're looking at a point where W cannot equal 0. Division by 0 would be undefined, so we don't have to worry about the undefined part of this derivative as far as finding critical numbers. Also, the endpoints are going to be unincluded in endpoints, so those endpoints don't matter, so there's no brackets on those endpoints. So no critical numbers from that. So the only critical numbers we're going to get is going to be where the derivative equals 0. And just like the last problem, we have a negative power on W. W doesn't equal 0, so multiplying by W to a power is legal. W squared gets rid of the negative power. So I'm going to do 72 W times W squared makes W cubed minus 200. W negative second W squared cancel, so W to the 0 just goes away, and 0. And then if I move the 200 over, I get 72 W cubed equals 200. So W cubed is equal to whatever 200 divided by 72 is. 2.7 repeating. And if W cubed equals that, then W is going to be the cube root of that number. So math 4 is cube root. And I'm just going to type in answer. You can go, if you go 4 decimal places, you're fine. But if you do answer, you're going as many decimal places as the calculator can hold. 1.4057. W represents the width. The dimensions are in meters, so that's 1.4057 meters is the width. That is the critical number of this derivative, right? Again, it's the only critical number, and typically, if it's the only critical number, probably that's the one you're looking for. But again, it's good to verify that. So if I set my intervals from 0 to 1.4057, and then 1.4057 up to infinity, picking a test point, let's go 1, 2 for test points. The function I'm testing is my derivative, so 72x minus 200x caret negative 2. Go here, type in 1 and 2. Oops. 1 and 2. Negative, positive are the results. Negative here, positive here, which means we go down, hit the critical number, then go up. That's going to be minimum. We can see, find the cost for the cheapest, so the minimum cost. All right. It asks for the cost of materials. So I figured out the optimal width, right? It's not asking me for the dimension of the box. It wants to know how much the box is going to cost me. So I'm going to go back to my cost function. Cost function is right here before we differentiate and figure out the actual cost. Okay. One thing that I have seen students struggle with in these problems, there's a lot of equations on your paper. Going back to the correct one each time is important. So when I was testing the derivative to figure out increase and decreasing, I'm testing the slope. So is it going down, is it going up, is it getting less decreasing or increasing? That's going back to the derivative to test. But to actually find the cost, we're going back to C. So 36x squared plus 200x caret negative 1, and type in 1.4057. This box is going to cost us $213.41. And the final step on that process I gave you yesterday was answer the question. So again, make sure that you read carefully to see what it is they're looking for. Are they looking for the dimensions of the box? Are they looking for the cost? Let's say you work for a company and you need to create containers to ship things in. You have specific requirements for these containers. You know, that's what you're looking for there. Hopefully it's something pretty expensive. For a box is going to cost $213.41. Hopefully we're shipping something that's pretty pricey. I've got this bubblegum machine here. I bought it at the store for $50. Can we ship it? Well, yeah. So anyway, just keep that in mind that you got to be careful that you answer the question. If it said find the dimensions of the cheapest such container, now we want the length, width, and height. You know, you've already found the width. Multiply by 4 to get the length, and do here 5 times W negative second to get the height. So you know, again, depends on what they're asking you to do.